Okay, so n is not less than n, therefore we can split our Rm into Rm minus n cross Rn. That is to say, a point x in Rn, we decompose x by xyz in Rm minus n Rn. Okay, and also our point P can also be decomposed in this way. P is AB, and also our H is KL. Here A is m dimensional, m minus n dimensional, B is n dimensional. For H, the K is also m minus n, and L is n dimensional. Okay, so this condition means that the condition that determinant Gij at P is not zero. Here, I from 1 to n, J from m minus n plus 1, m means that the derivative of G, which is get back to y, to the last m variables at the point P is invertible. Okay, can you see that? This condition that the determinant is not zero means that this metric is invertible. But this metric is this metric. Is this submetric of the G prime P. This submetric is precisely the partial derivative of G, which respect to the to y. Sorry, I make a mistake here. Our x is zy, no yz. Sorry. Z is m minus n. The last n coordinate of x we denote by y. Okay, so this means that the partial derivative of G with respect to y at the point P is invertible. So what we have our condition is that GP is GAB is 0, and the derivative of G with respect to y at this point P, that is AB, is invertible. Invertible means that the determinant is not 0. Okay, so we can apply the implicit function theorem by the implicit function theorem. By the implicit function theorem, we draw a picture. This is Rm minus n. This is Rn. Altogether is Rm. And our A is here, and our B is here. So this point AB is a 0 point of G. So by the implicit function theorem, we can find a small neighborhood of A. So it's a neighborhood of A. Okay, a small neighborhood of A, and a map defined in the neighborhood of A to Rn. So we have an epsilon very small, and a map phi defined on the epsilon neighborhood of A. This is in Rn minus n. And map into Rn. The graph of this map phi is this curve. I draw in the picture. Maybe I use red. Maybe. So this is the curve. So this is the graph of phi. Okay, so we have such a phi such that phi a is b. The value of phi at the point A is b. Phi a is b, and the gz phi z is 0 for any z in the neighborhood of A. This is precisely the conclusion of the inverse function theorem. Okay, and we also know how to compute the derivative of this implicitly defined map phi. We know that phi prime A is minus the inverse of G with respect to Y, because this metric is invertible. Invertible. Okay, the metric is invertible. Then multiply by the metric with respect to Z. So this is the formula for computing the derivative of phi at the point A. Okay, so let's have a summary. Our condition of the proposition means that for our map G, GAB is 0, and the partial derivative of G with respect to Y at the point AB is invertible square metric of order n, because the determinant is not 0. Okay, so we can apply the implicit function theorem to obtain a map defined in the neighborhood of A, satisfying the following condition. The first is that the graph of the map passing the point AB, that is phi A is B, and the second is that the point near for points Z near A, the graph make G to be 0. So that is GZ phi Z is 0. So this is precisely the conclusion of the implicit function theorem. And we also know how to compute the derivative of phi, which we have done in the last lecture. So the derivative of phi at the point A is the inverse of the derivative of G with respect to Y multiplied by the derivative with respect to Z. Okay, so we will use this phi to construct our curve gamma. To construct our curve gamma. So we defined gamma from an epsilon neighborhood gamma t is Rm is Rm minus n Rn. So to define the curve gamma, we need to define the two components of gamma. The first component is n minus n dimensional. The second component is n dimensional. Of course, we will use the point AB, and we will use the point AB. P is AB. B is n dimensional, and H is KL. Okay, so we will use this data. So our gamma t is A plus TK, but the last n coordinate of our curve gamma will use the image of A plus TK under our map phi, because phi is mapped into Rn, right? So we can use this to define phi A plus TK. So obviously this gamma is smooth, because phi is say 1, so gamma is say 1. And gamma 0, what's gamma 0? Gamma 0 is A phi A, that is AB, that is our point P. So this is a curve passing the point P. and the derivative of so gamma passing p this implies that the curve gamma passing the point P. We also have g gamma t. What's g gamma t? G gamma t is g a plus tk phi a plus tk. So you consider the a plus tk to be z, right? Then this is gz phi z. If t is very small, and then a plus tk is also very close to a. So for z equal a plus tk very close to a, with phi z gz phi z is 0. Okay. So this means the image of gamma lying in the set gamma t belongs to the inverse of 0 for any t small. Okay, maybe not epsilon. The range of t maybe will be smaller than epsilon. How small the t will be? The t will ensure that a plus tk belongs to the epsilon neighborhood of a. So this means the norm of tk less than epsilon. So the range of t will not be minus epsilon. T will be, if t is in the minus epsilon over the norm of k, epsilon the norm of k. So for t in this range, in this interval, our conclusion is true. Of course, if k is 0, then t can take any value. If k is 0, you could not, the norm of k will be 0, so you could not put the norm of k to the position of a denominator. But when k is 0, this is automatically true. Okay, so if the k is 0, we don't need to do anything. But if k is greater than the k is not 0, then we can take t in this interval. Okay. Anyway, we construct a curve gamma defined in the neighborhood of 0, so that the curve gamma passing the point P when t is 0. And also this curve lying completely in the set we are considering. So it's sufficient to prove that the derivative, the tangent of this curve at the point P, that is the derivative of gamma at 0, is the given vector h. So our problem is to find, so that there is a curve. This curve need to satisfy two conditions. One, the curve need to lie in the set M, that is the inverse of 0 and the map G, and also passing the point P and which tangent h. This is what we want to prove. But now we know that our curve gamma constructed above, passing the point P and also lying completely on the set M here. That is the inverse of 0. So we only need to prove that the tangent of the curve is h at the point P. But how to compute the derivative of this gamma at 0? But of course, you need to compute using the definition of gamma here. Gamma is given in this formula. So to compute the derivative of gamma at t equal to 0,